So here, what is going on? Stop. Go away. All right. So all right, this one is probably best done by like eliminating the options until you're left with, okay, guess that has to be the one, since it's asking which of the statements are false. So the first one is the limit as x approaches 1 of f of x is equal to 0. So I find the graph of f of x. Left-hand limit's going to 0. The right-hand limit's going to 0. That seems fine. The limit as x approaches 2 of g of x does not exist. So going to 2, that's limit is 1. And going to 2, that limit is negative 1. Okay, I agree that does not exist. This says the limit as x approaches 1 of f of x and g of x plus 1. So that would be the limit as x approaches 1, which looks like 0. And the limit as x approaches 2, we said does not exist. But is 0 times does not exist? Is that 0? Is that does not exist? Maybe not entirely clear. And the last one here says the limit as x approaches 1 of f of x plus 2 times g of x plus 1. So f of x plus 2 is, or f of x plus 1 is just at 2, so that looks like the limit would be negative 1. It certainly exists there. And g of 1, or the limit as g approaches 1, well, that's looks like just 1. That certainly exists there. So the one that would be least convinced of would have been C. So that's how I would have ended up at C, because I would have done that by process of elimination. If I got to one, it's like, is that false? I don't know. Does not exist times 0. Is it 0? It does not exist? I'm not sure. Let's see what the other ones are, and if I'm convinced all the rest of them are true, that one must be the false one. Does that feel okay, Paul? Okay. Yeah, that one would have been, again, rather tricky. I think that's seeing what else is going on. Do you guys want to look at either 1 or 9? Those are the other two that I think were most frequently missed. 9? This guy? Yeah. Okay. So the big idea here is that whenever we're talking about so velocity with respect to position, right? S of t is the measured in feet and t in seconds, so it's like the position. The velocity is going to be the slope of our position function. Everybody's okay with that? Because it's like the rate in which position is changing. So you're really looking at either C or D then, right? Because those are the only two that are representing as slopes. Everybody's okay with that? Of those two, if you want the slope at 8, the better estimate is going to be the 2 points that are closest to 8. So if I'm using 9 comma s of 9 and 7 comma s of 7, those are much closer to the point, or when t is equal to 8, than 2 and 12, right? And that's it. That's all I'm looking at. It's just like, if I'm looking at a slope, my best estimate for the slope are going to be using the points closest to the value I'm looking for the slope at. That's it. It was almost the exact same question as one of the other ones. It just was in words and written as a like velocity position kind of thing rather than a like slope of a tangent line question. But it's ostensibly the same thing. Any of these other ones we want to talk about? Sure. So we're given this table of values, asks for the limit as x approaches 2 of e to the negative 2 times f of x. So one of our limit laws says that we can take, if we have like a composition of functions, we can take the limit of the interior function, which is what we're going to do. So using the table, I'm going to find the limit as x approaches 0 of f of x, and then plug that value into e to the negative 2. So if I look at the table here, from the left, we're getting closer and closer to 0. And if we look at the limit from the right, again, we're getting closer and closer to 0. So here's the limit of as x approaches 0 of f of x is 0. So e to the negative 2 times 0 is just e to the 0, which is 1.
Oh, I see.
Because anything to the 0 power is 1. Okay. And the rest of these, it seemed like the vast majority of us were okay with. I don't know if there's a way for me to post any of this, like with the answers on it attached or not. Oh, they gave you the answer? Okay. After it finished or whatever, if you want to go back and look at it. Okay. So if there's any other individual questions, we can just handle those individually. Does that sound fair to you guys? Okay. All right. Do you guys have, Sophia, homework question? What page? Or what section, anyways? 2.2, number 21. So the directions here say guess the value of the limit if it exists by evaluating the function at the given numbers correct to 6 decimal places. So 21 says the limit as t approaches 1 of e to the 5t minus 1 over t. Oh, it does say in my book too. I just misread it. Okay, so I'm going to do this entirely on the calculator because it's giving me a bunch of values. Is that cool with you? Okay. I just hate that I can't get rid of this stupid bar. Anyways, I'll have to figure that out sometime. All right. So alpha y equals, I'm going to type in my function. So e to the 5x minus 1 over x. And then I'm going to go for vars, y vars, function y1. And then I'm going to do the left-hand bound first. So that's negative 0.5. And then negative 0.1. And then negative 0.01. what do you notice is happening here? Oops. 0.001. Well, it's certainly increasing the whole time, right? Yeah. Let's see, 0.001, getting closer to 5, as you suspected. So certainly appears the left-hand limit is going to 5.
Yes.
And then we just would have to check with the right. Just get rid of that. Make that a 5. Get rid of you fellas. So just do the same thing, see if this decreases to 5. Certainly looks like it's heading that way, doesn't it? So that's all we're doing. And again, this is like an entirely on my calculator kind of question. So pretty convinced we're going to 5 there. You agree?
Yeah.
Okay. Victoria. 13 and 14 for this same section. Okay. It says use the graph of the function f to state the value of each limit if it exists. If it does not exist, state y. Okay. So again, this is going to be one that I'm just entirely using my calculator to do. So it's first one. So the 3 limits we're looking at is x approaching 0 from the left, from the right, and then just the limit as x approaches 0. So that's that. Let me look at my window. Let's just zoom standard that for now. Okay. So I'm going to probably zoom in between -1 and +1, and then maybe like -1 and +1 on the y-axis as well, since it seems like this is a fairly well-behaved function, except for whatever's happening at 0 here. If I really wanted to get see what's going on, maybe I'll turn the axes off. So it appears that for part A, it's going towards 1. For part B, that's where it's approaching 0 from the left, that's going to 0. And because the right-hand limit and left-hand limit disagree, part C does not exist. So I just, well, the way I set my window was the top of the scale was 1, so it looks like 1 to me. Is that? Yeah, I turned off the axes so that I could see the gap in between them, just to make sure that nothing funny was happening. But we still, Victoria wanted to see 14 also. Mackenzie, is this a follow-up to this one?
No.
Okay. You think you're good with 14 after seeing what we did here?
Yeah.
Okay. Mackenzie, then? 2.2, number 39.
Yes.
Okay. Says determine the left-hand and right-hand limits of 1 over x cubed minus 1 by... I think you actually are using the newer book, because I'm looking at the older book right now. But when you say the old book, you mean the original 8th edition that I posted, which is actually the newer book than the 7th edition, which we're using. So that's why I was confused at what you were saying there. So I reposted the digital textbook to the 7th edition, which matches the paper one that people have issued. That's the one that we're going to be using from here on out. If you didn't do the 7th edition problems, that's okay. You don't have to change anything. But from here on, let's try to just use the 7th edition. Okay. Yes, Mackenzie, we can do whatever you're talking about. Can you read it to me? X times cosecant. Oh, sorry. Okay. Okay. That's what we're doing? Okay, does it give any directions as to how they'd like this to be done? Okay. So let's just look at the graph then. That's as good a place as any to start. So remember that cosecant is 1 over sine x. Actually, let's just write it this way. All right, that's a trig identity. They'd expect you to remember that basic of 1. I have the x in the numerator, right? Is that okay? All right. And then I'm going to do zoom trig, which will reset my stuff there. And probably going to turn our axes back on so I can tell where negative 2 pi is. And we're probably going to actually go from, let's do negative, oh, that's 2 pi from the left. Sorry. So negative, let's go 0 to 4 pi. Does that feel okay, Mackenzie? All right, just so that the 2 pi will be right there in the middle for us, which would be half, 1, 1.5, 2. Radians, okay. Where's the rest of my stuff here? All right, well, just go look at this then. Okay, I just need to extend my graph then a little bit. That's fine. Do that. There we go. So this is negative 2, or I'm sorry, 2 pi is right here. If I'm looking at the left end of it, looks like it's going to negative infinity. Is that, took a little shake into the graph or the calculator to get the graph or get a decent picture to come out for me, but
yeah, that's why I was going to see the graph. So wait, how do you know about that sort of thing?
because this is 2 pi right here. Right. So I'm going to take the left side of the graph, which is that end, which is the one that's going down to negative infinity. Anybody else? Questions on things? Paul? Sure. What's up? 39 in the other, from the other version. Okay. So the other 39 says to determine the limit as x approaches 1 from the left and the right of 1 over x cubed minus 1. And it gave us some instructions as how to do that. It said by picking values as approach 1, and then by reasoning, and then from the graph. So let's start that. Okay. So I'm just going to use these same values of x that we had used in that problem for 21. They seem like reasonable x values to me to use. So we're getting closer. Oops. So this, at this point I'm stopping, right? Looks like it's going to -1. From the one end. Let's check the other end. And at this point, I'm going to be pretty convinced that that's going to -1 also. Agreed there? So that should be good for part A. It said by reasoning as in example 9. So I'm going to flip back real quick here and look at example 9 on what they did. Okay. All right. So x approaching 1 from the left, we're talking about numbers that are, oh my goodness. Elvis, look at the values I picked for this. Look where my limit's going to.
Oh.
Yeah, that's Mr. Kulik's boogered that all up.
I was gonna say it already had the limit there. So.
Yeah, that's Jeepers Creepers. All right, let's do that. So 0.9, 0.99, and I shouldn't be negative either, Mr. Kulik. What are you doing? I don't know. It's early. I don't having a bad morning already. All right, so this one looks like it's bombing off towards -infinity, right? Does that feels a bit better, I hope, right? Okay. And if I think about that, if I'm picking numbers that are smaller than 1 and I cube them and then subtract 1 from it, I'm going to be getting a negative value. And that number down here should be getting really, really small, which should be sending me off to -infinity. This is me doing part B as long as I'm at it. If I do the same thing here, and I pick numbers that are slightly bigger than 1, when I cube them, I should get another number that's, again, slightly bigger than 1. So when I subtract 1, it should always be positive. And as that number in the denominator gets super small, we start shooting off towards positive infinity, which is what we're seeing here in my table. And if we had looked at the graph, we get the left end going to -infinity and the right end going to positive infinity, which is what we observed from the other two methods. Does that feel better? Once I started using the correct values anyways. I was looking, I was like, why am I getting like -1? That doesn't make any lick of sense. But I didn't question myself. I just kept going because they matched. I'm like, oh, okay. There's going to be something that's like, no, you're just doing it wrong, you moron. Yeah, that's it. Sorry, guys. Doesn't help. Yes, Victoria. Uh-huh. So does yours read, use the graph to estimate the equation of all the vertical asymptotes to the curve tan of 2?
Yeah.
Okay. All right. So where is tan of x undefined at? Okay. What can you use to check if you don't remember? Yeah, let's just look at the graph, right? So I'll do zoom trig and just see what we get. So again, each one of these is half a pi, so it looks like -half a pi and +half a pi give us undefined, right? Everybody agree? Now my pen doesn't want to work. I've been a bad tech morning. So okay. Everybody's okay with that. And really what we want is, so I need this part to be equal to pi over 2, right? So the sine part needs to equal pi over 4. So x should equal to sine inverse of pi over 4. And that should be happening every pi, right? Is that right? Let's go look at the graph. That'll help me. Look at this crazy thing, huh, guys? So let's see, I got 1, 2, 3, 4, 5, 6, 7, 8 asymptotes from 0 to 2 pi. So we should be getting 4 4 asymptotes. Well, that's 4 pi length, right? So it should be getting 2 asymptotes per pi, 1 at each end. So that's right. So this is just plus pi k, where k is an element of the integers. And just for the record, whatever sine inverse of pi over 4 is, that should be my value. So that number, whatever that is, that's my angle in radians. Oh, it also only wanted us to go from negative pi to positive pi, right? So there's like here's like the 0.903. So we got 1, 2, 3, 4 inside of pi. So that's not right. So we have this. So we have this one, and then we have this one that'll be at the same spot, but it's minus pi units, right? Yeah, so that was fine. But we have another set, because sine inverse, or sine is positive, let's think here for a minute. Let's try this. 0.90. What if I do it this way? What if I do sine inverse of pi over 4? So, yeah, okay, so good, that worked. Okay. And then what if we do sine inverse pi over 4, and then we do minus pi. Okay, so that's this spot over here. So that what we're doing so far looks good. Okay, and then we'll try sine inverse of pi over 4 plus a half a pi. Oops. Yeah, that'd be fine. So that's missed that one. So there's another one here, right? Oops. I bet it's this is my other one. Yeah. You see why? We did negative pi over 4. Why was that going to work? Because it's undefined at pi over 2 and negative pi over 2. So I have this plus pi k after it also, and that should take care of everything, I think. How's that feel, Victoria? Is that good enough? Okay. All right. Where did we leave off last time? This is the problem with the weekend, right?
Yeah.
The squeeze theorem. We finished 2-3 then, huh?
Yeah.
Okay.
have a question. How many sections are this check?
I don't remember, 8, 9, something like that.
A while.
We got a while. Okay, although we are skipping 2-4. Because 2-4 was all just like epsilon delta proof stuff, which is beyond the scope of this class. We talked about the definition, the epsilon delta definition, really what it was saying. But then I said that I wasn't going to have you do anything with this because it's beyond the scope of the class. So what we're going to be talking about in section 2.5 is continuity. We say that a function is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. So this is like continuous at a point. Now keep in mind this definition implies 3 things, right?
Oh, there is a limit. I just felt like the stupidest person ever. The number has to be continuous.
So it implies a is in the domain of f of x.
And not get any sleep last night.
That the limit exists.
I was right, so.
And then that it's actually equal to this. So for example, if we were lacking number 1, something like this, we don't want to call continuous, right? Everybody agree?
If the circle was filled in, would it be continuous?
Yes.
What's wrong with this one?
It's 2 slots that point's not.
It's not defined at a, right? The function is not defined at a because a is not in the domain of f of x. Now, what if if we had this? What part fails now? Is this continuous?
No.
Still not, right? What part fails? Part 3. Because the limit isn't equal to the definition of the function. This point up here is f comma f of a, right? Or is that a comma f of a?
Yeah.
That's that point up there, which is definitely not what the limit is equal to. Everybody's okay with that? And then the limit existing is obviously means that the 2 ends of the graph have to match up at the point, right? Does that feel okay as to like what's what we're saying? Okay. So what we're often most interested in are the discontinuities. So the places where the graph fails to be continuous. So let's say we have this one. Should be able to do this just using your Algebra 2 knowledge. What would we want to do with this? I would do something first before I do that. Yeah, we should factor this. Notice that these reduce. And is what I've written here correct?
Yes.
Nope. Those two things are not equal all the time. Where are they not going to be equal at? When x is equal to 2. Tricked you. Everybody's okay with that? Does that ring a bell?
Does ring a bell. Yeah.
Oh, you saw it.
You just kind of did x minus 2 equals 0. Then
Because if I did f of 2 here, that's undefined. If I did f of 2 here, you would have said it's 3.
right.
Right? Those are not equal. So the two statements I made were not equal. I had to include this so that,
It's in the bottom.
right, because we,
Non-mentioned.
yeah, do you remember what it's called when that happens?
No.
This was the removable discontinuity.
Remove this continuity. There we go.
When you can completely reduce a factor from the denominator, that factor creates a removable discontinuity. So if you wanted to look at the graph of this,
Yeah, wait, Mr. Bullock,
yes,
with that logic, can you just plug in like any?
So wait, how do you know it's undefined again? You plug 2 in.
if I get a zero denominator.
Oh, right.
This is it.
Oh, okay. Let's get the questions one at a time, okay? I'd be happy to answer all of these, but it's getting a little difficult for me to think, and I'm sure it's getting difficult for others to think. Paul?
So does this mean that anything in the denominator is going to not be part of the answer? Like it's not going to, you're gonna have to do backslash.
Those will be sources of, they will not necessarily be removable, but they'll be sources of discontinuity. Victoria,
Where did you put
where did I put what?
like
The whole? Well, it's going to be the x-coordinates 2, and when I put 2 in for that, it would have been 3, right? So it should be that removable discontinuity should be at the point 2, 3.
Okay, wait, so why did you put 2 into F box?
Because that's where the hole is.
That's one of
So we're searching for the discontinuities, right? So the place where the function is undefined. So if my function has a fraction in it, the only way a fraction can become undefined is if the denominator is equal to 0. So clearly 2 is going to be a discontinuity here, right? And I wanted to point out to you that if I factored this and reduced it, what I noticed is that 2 is actually a removable discontinuity. That means it's just going to create a hole in our graph like this. So to find the location of that hole in my graph, I can take the value of the discontinuity, which was 2 in this case, and then plug it into the reduced version.
Okay.
That gave me the y coordinate.
I understand.
Does that
Yeah.
all feel okay? So clearly here we have a function that's discontinuous at x equals 2, since 2 is not in the domain of the function. Taylor?
So when you ask like find the discontinuity, are you just looking for the 2, or are you looking for the whole like x plus 1 and then x is not?
No, x equals 2 would be the discontinuity. Yep, that would be fine. I wanted to do that this way because what I'm going to do next is I'm going to define this piecewise function. Now, is 2 in the domain of our function? Absolutely it is, right? It's definitely defined for 2. You guys all see that? Is this going to be continuous though, even though my function is defined on all real numbers? Well, remember, this is what the top part looks like, right? And then if I graph the bottom part, I'm graphing the point 2, 1. Everybody agree that that's going to be what this piecewise function looks like? Is this continuous? No. Because the limit, as x approaches 2 of f of x, does not equal f of 2. So we're still discontinuous. At x equals 2, but this time we know that the limit as x approaches 2 of f of x is equal to 3, which is not equal to f of 2, which was 1. Does that feel okay?
So
Correct. Yep, the third kind of part of that.
So the way you wrote it, like the limit as x approaches 2 of x, so it equals 3, which does not equal f.
Because that's 1.
Because f2 is 4.
Right? When I plug 2 in for f of x, I get 1.
And then where's the f of x equals 3?
So if I'm doing the limit as x approaches 2 of x plus 1, which is what this simplified down to, right? That's just 2 plus 1, it's 3. I can just use direct substitution to evaluate that.
Oh.
Or you could look at the picture that we drew. Right. That would be fine also. Is that okay?
Yeah.
Everybody feel Sergio?
Just sorry to backtrack, but I just don't understand why x is not equal to on top. How do you know like right now?
Simplifying this,
Right.
well, Because if I take this and plug 2 in, I get undefined. Correct? Because you get a 0 denominator.
Oh,
If I take this and I plug 2 in,
you get
it's not undefined. So they're not equal.
right.
They're equal everywhere except for
Okay.
where that
I was just like, how did you know that? That makes more sense. Okay.
Victoria.
But, okay, wait, maybe I heard wrong. Did you say something like if you plug in a student, example, did you say like if you plug in 2, you get 1?
Right. That's what this piecewise function is saying. It's saying if I'm doing f of 2, I look at, okay, what do I do when x is equal to 2? I get 1.
Did you just say that was undefined?
In it, part A is what Sergio is asking about. Yes. There are 2 different problems that are really similar, because I'm just trying to point out to you like the sneaky things that people can do to try to trick you into thinking something's continuous when it's not. Right? Is that okay? So the sneaky thing here is remembering that even though you've reduced this, it's not at 2 is not in the domain. Okay? Very easy to just reduce that and make it or make it equal to x plus 1 and go, oh, sure. You know, if I plug 2 into x plus 1, I get 3, and I can take the limit as x approaches 2 of that. They're both the same thing. Right? Very easy to make that mistake and forget that just because you reduce that out of there, you still have to keep, in mind that 2 is not part of the domain. That this was still a rational function at the start and not a polynomial function. That's okay? All right. So some nice rules about continuity. Oh, actually, we need to do something first before I do that. Okay. So some more definitions. You can have continuity from the right. Or you can have continuity from the left. Where would continuity or continuity from the right or continuity of the left become particularly important? Let's say we have a function like y equals the square root of x. That has a decided beginning at 0, 0. So here at 0, 0, do we have continuity from the left? No, because the limit from the left doesn't exist. However, we are continuous from the right, since the right-hand limit would equal f of 0, right? So this, we would say, has continuity at the right, or from the right. Okay, so if you have like a function like that that has a decided start or end to it, piecewise functions also, all over the place, are going to have that kind of like one-sided continuity, or possibly have that one-sided continuity. Is everybody okay with this idea? All right. So, another definition. I want to talk about a continuity on an interval. So we say a function f is continuous on an interval What do I mean by an interval? Like a big stretch of x values, right? Like all the x values from like -2 to +5 would be like an interval, right? What's the biggest interval possible?
Any positive.
All real numbers. Very good. Just reviewing, right? Okay. Now the one little thing to kind of keep in mind with this definition is, let's go back and think about this example that we looked at just a moment ago. Here, we would say that f of x, I guess we should call it f of x, huh? Here I would say that f of x is continuous on the interval 0 to +infinity. Oops. Because when we say continuous on the interval, if we have an endpoint like this, when we say continuous at every number on the interval, we understand that to mean, like, for a function like this, if it's only one-sided, that we really mean like left, like continuous from the right or continuous from the left at that endpoint, whatever it needs to be. Is everybody okay with that? So we would still say this is continuous over its entire domain, even though at 0 it's only continuous from the right. But because the function isn't defined at, like there's no more function before that, it's okay. Is that all right? Okay.
This feels like a bad question, but the bracket means including, right?
Correct. Yes. Let's do an example. Okay. So it says show that f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to +1. First thing we need to check is if I take some a from that interval, is a in the domain of f of x? Everybody's okay with that? So what kind of function is f of x? It's a square root function, right? Where can we get in trouble square rooting things? What? Not everywhere. Negatives, right? So I know that for the values of x to be in the domain of f of x, that stuff underneath the radical must be non-negative, right? So if I solve this for x, subtract 1 from both sides, divide by the negative, square root both sides, we get x is plus or minus, or x is less than or equal to plus or minus 1. But right here, is that correct? Nah, man.
Open up, because you can't spur something have a negative.
Nah, man. So if I think about when is x squared, here's my x squared, here's the value 1. Where is that function less than 1? It's right in here, right? So really we mean x is less than or equal to 1, or x is greater than or equal to negative 1, which is exactly this, right? So good, we're in the, anything we pick from that interval is certainly in the domain of our function. Everybody's good? The next thing we need to do then is to show that the limit as x approaches a of f of x is equal to f of a. That's the second thing then we need to show. Everybody's good? Okay. So the limit as x approaches a of f of x is equal to the limit as x approaches a of 1 minus the square root of 1 minus x squared. And I'm going to just like do this so it's clear that the limit is applying to the entire thing. Okay, everybody still good? From here, I'm going to go and do limit laws. Everybody good with that? So first thing I can do is I can distribute my limit to both parts of that function. Everybody's good with that? What's the limit as x approaches a of 1? 1, very good. And with that second piece, I know that the limit of a composition is like the composition of the limits. So I can go and I can pull that limit underneath the square root. Everybody's good there? And then I can distribute again. And now if I evaluate, I have 1 minus a squared. And what is this equal to now? That is specifically f of a. If I plug a in for f of x, I would get exactly that. So we're done.
Can you do multiple steps in one? Like, do you have to write, like, for example, for like the first two, could you just write it all under the parentheses?
Yeah, man, but these are nodes,
Okay.
right?
But you won't care if you do.
Within reason.
Like, I won't combine all of the steps into one, but like just putting it under the parentheses.
Putting it under the parenthesis.
No, the square root of it.
Oh, yeah, if like you combine these two steps.
No, like that, the first two steps.
The first two steps? Yeah, I mean, that seems fine. What's up?
How did you go from the second to last step to the last step?
this to here?
No.
Well, my function f of x is this, right? If I plug a into that, I'm just going to put an a in for the x, which is what I had, right?
Oh.
Is that okay?
Oh, yeah, that's okay. I got it.
You got it?
What's the squiggle on the box?
That's like the end of your proof symbol. It's just a filled in box.
Oh, okay. I thought that was an actual math term, like a sci-fi, a horizontal theory or something. I was like, wait a minute.
No, correct.
Awesome. Thank you.
All right.
What's the box mean?
Just the end of your proof.
By the way.
So this theorem right here is quite useful.
Like stuff.
It says that if f and g are continuous at a and then c is a constant, then f plus g, the sum of two continuous functions, is continuous. F minus g, the difference of two continuous functions, is continuous. A scalar times a continuous function is continuous. The product of two continuous functions is continuous. And the quotient of two continuous functions is continuous, provided that the denominator is not equal to 0 at that value a, which is like quite helpful. Particularly when we combine it with this theorem.
Explain the function. Like the that's a plus minus.
That's not equal to.
Oh, that's fine.
So if I take a polynomial and I add it to a rational function, what can I say?
Continuous everywhere.
Nope. It's continuous on the domain of the rational function, right? Because that's the more restrictive environment. You can certainly say it's continuous at the domain of the rational, right? If I take two polynomials and I multiply them together, it's continuous everywhere. The result is continuous everywhere. So you see how I can use these two theorems in conjunction to really say something quite powerful?
Yeah.
Like
That's a real punch.
you can now, because you know that polynomials and rational functions are continuous on their domain, and then you know that the sum, difference, product, scalar, and quotient of continuous functions is continuous, you can really kind of piece these two together to say quite a bit about a function just by looking at it, because it's easy to identify polynomial and rational functions. Yeah, Sophia.
Are we gonna use these to like prove that something is like?
You could certainly use it to shortcut through a lot of work. Yes.
It's probably my favorite thing you said all day today.
Yeah. So depending on the direction would matter there, Sophia, but like if it just says show that this thing is continuous at point, at a equals 5, you're like, yo, the thing is a polynomial, so I know it's continuous at that value and all the other values. You could do that. Now it says if it used the definition of continuity to show that this thing is continuous at 5, then you'd have to do that. But at least you know what the answer is, right?
So this is dealing with the continuity as well. So then let's see. The continuity and also the polynomial.
Yeah.
Okay, gotcha.
So here gets even better though.
Oh, awesome.
All right. These functions are also continuous on their domains. We have polynomials, we have rational functions. We have root functions, like square root, cube root, etc. You have trig functions. You have inverse trig functions. You have exponential functions. And you have logarithmic functions. Basically, everything that you've seen from Algebra 2 and Trig and Pre-Calc constitutes a continuous function. And if you combine them together, still continuous, right? Over the domain of, like, the intersection of the domains. Which is quite helpful, right? Okay. Another theorem. Again, these next two I think are quite useful.
Excuse me.
Okay, again, what we're saying here is that providing that you have the pieces are continuous in the way that you need them to be, the limit of a composition is just the composition of the limit. Which taken with this taken together, we can then say if G is continuous at A and F is continuous at G of A, then F of G of X is equal to, we should say that is continuous at A. What's that saying? Is that the composition of two continuous functions should be continuous. And we will finish this guy out next time with the intermediate value theorem and close this chapter, or close this section out.